Rutgers, and where he is now a distinguished professor of physics. He's working at the overlap of particle physics and condensed matter physics, and he's famous for applications of different integrability methods to solution of a range of important physical problems, in particular Kondo problem and the chiral Gross-Neveu model. He is a member of American Physical Society and a recipient of Lars Onsager Prize of APS. Today, he will tell us about Kondo effect in superconductors. So thank you very much for contributing to our seminar. And let me just once again confirm Valdelino that we can start. I'm sorry for this technical delay.
Yeah, I'm sorry about that.
Valdelino? Okay, thank you very much. The word is yours, Natan.
Okay, thank you very much. Thank you, Dimitri, for the invitation and for the nice introduction. And it's a pleasure to give a talk in Brazil, not as much as visiting, but it's still very nice. So I'll be talking about Kondo effect in one-dimensional superconductor, a work which I've done with 3 collaborators. Patrick Azaria is a professor in Paris. Colin and Parmesh are students of mine. Both of them have graduated. So let me remind you what is the Kondo effect in a regular metal. So one puts here, do you see me? Do you see my slides?
Yes, we see everything. We can see your pointer as well.
Okay, so the Kondo effect corresponds to screening of the impurity, the red dot, with a spin by the electrons around it. So we have the metal Hamiltonian, which is the Fermi C, which is a free field. And the electrons interact with an impurity, as impurities typically spin half, via density, spin density interaction. This is the spin density of the electron at the position of the impurity, which I just take to be at x equals to 0. And the Kondo effect is a dynamic screening, and you can see here sort of the cloud of electrons around it, where you have more spin downs than an up. And the screening of the impurity can be summarized nicely in this diagram. So at high temperature, you see that the susceptibility of the impurity here at high temperature behaves just like a free susceptibility. So at high temperature, the impurity susceptibility tends to the susceptibility of a free, namely 1/T behavior, with logarithmic corrections on the scale Tk, logarithmic corrections that decay very slowly as the temperature is increased. When we lower the temperature, on the other hand, then instead of the susceptibility diverging, it crosses over and is finite, indicating that you have screening of the susceptibility. So this is the weak coupling regime, where the impurity interaction with the electron behaves almost like very weak coupling, while here the coupling is so strong that the impurity is completely screened, and we can see that it is screened by the fact that the susceptibility is finite. And the scale Tk that emerges, which characterizes both high temperature and low temperature, is Tk, this is D is the cutoff, e to the minus pi over 2j, a non-perturbative cutoff that emerges. And the density of states of the impurity, of the electrons around the impurity, is also characterized by this K, Tk over E squared plus Tk squared. So this is the standard Kondo effect. Question is, what happens when instead of putting an impurity in a gas of free electrons, namely a metal, we put it in a BCS superconductor. So this is a very old question. As you see, it already, people started working in 1965. And how to do now the calculation of the screening and interaction of the impurity with the now gas of BCS bound states is not a trivial question. Now the Hamiltonian has, in addition to metal and an impurity, has also a pair interaction which drives superconductivity. So we have here side dagger, up, down. This is the Cooper pair, and delta is the band, is the gap. And this represents the theory in a BCS mean field theory. So now we have a competition between the screening and Cooper pair formation. And the YSR approach was to use mean field and classical spin as follows. So what you assume now is that the spin is very large and doesn't fluctuate. So you take the limit where J times S goes to infinity, suppressing spin fluctuation. And also you are using mean field to describe the electrons. And what they found is that we'll have bound states at the site of the electron, which is going to screen at the site of the impurity, which is going to screen it. So you have a bound state, which is a function of the phase, where delta is the gap, sine of 2 alpha of J, where 2 alpha is pi over 2 minus Js. So you see, if this here is the gap, delta, in an energy gap, we have bound states at the impurity site, sub-gap bound states. This is a bound state which screens the impurity, and this is a bound state which does not screen the impurity. And you have a first order transition between these two phases depending on the strength of Js. And more recently, people improved this, introducing a quantum fluctuation and renormalizing this phase. And there are people are interested in this YSR state because they are trying to realize a topological helical chains by arranging this type of impurities on superconductors and using them to realize topological and Majorana edge modes. Now, the question that we ask is, if we take, so the BCS is a good theory in 3 dimensions, and mean field theory works for BCS. But what would happen if we want to understand the Kondo effect in a superconductor with strong fluctuations? And we are going to look at a charge conserving. The BCS, the charge is not conserved because each pair is psi dagger, and we have expectation value of a charged order parameter. But in actuality, the superconductor is charge conserving, and we want to understand what will happen when you do interactions of the impurity with a one-dimensional, strongly fluctuating superconductor. So the model that we are going to study consists of the following Hamiltonian. This is the Hamiltonian of the bulk of the superconductor. So we have left and right moving electrons on a system between minus L over 2 and 0. So this is the left and right mover. And here is the interaction which is called the, so you see we have a side dagger, and right, side dagger, left, and they interact and open a gap. This is a superconducting gap, but now it's generated by the interaction themselves, while before we put it in by hand when we talked about the superconductor. So this model, in its anisotropic, so you see there is G parallel and G perp. The model is anisotropic, and this was I solved it in the isotropic line, as you see here, and Gia and collaborators solved it in the anisotropic case. So as you see, the model flows in RG to, in the isotropic, in anisotropic case, it flows to strong coupling and opens a gap. So all this work was done with periodic boundary condition. Now we have to do to work with with periodic. Now we have to work with open boundary condition, and what we'll find is that we wrote papers on that do not about the superconductor but the model itself, and we showed that the model in the region that I call A is topologically trivial, while in the region that I call A hat is topological, namely edge modes would appear in it, and it has non-trivial expectation value of a string, a non-local operator. And there is a crossover, there is a phase transition as we are changing G perp from positive to negative. And in this region, the model is spin singlet superconductor, namely the expectation value of the operator psi dagger L sigma y psi L is the slowest falling, while in this regime here, it is the spin triplet superconductor, and the correlation function with sigma x is the slowest falling. So this model is very rich. It has a charge spin separation, namely the gapped modes don't carry charge, but they carry spin. These are the spinons. They separate from the holons, and we have the order parameters that fall like x to the power half. So this is the bulk. Now we couple it to a local impurity at the edge here. So in addition to what we had before, we now add an impurity. Now, we are going to take G parallel equals to G perp equals to G. In other words, we are going to solve it on this line here, which is topologically trivial, but I will show later on that we can make the whole system topologically non-trivial and superconducting. So this is the model. So we have left-right movers. We have open boundary conditions here, namely an electron that moves to the right is scattered back to the left and vice versa at the other edge. And it's a spin dot spin density interaction. And the model turns out to be integrable for any values of the G, the bulk interaction, and J, the impurity interaction. By the way, I would appreciate questions. Can you hear me, by the way?
Yes, we can hear you. So
okay.
If there are questions, you can raise your hand.
I just wanted to make sure that I'm...
Yeah, sure. Yeah. We're here.
Okay, great. All right. So what is the physics that we are trying to capture? So as I say, this problem has been around since the 60s, and people were saying, well, you have two scales. One is the TK, and one is which describes the impurity, and one is delta, which characterizes the bulk. So if Tk is very large compared to delta, you assume the Kondo interaction dominates, and then you have other regime where Tk is of order delta or Tk very small compared to delta. But actually that is a bit confusing because, as I'm going to show, Tk occurs only in this regime here, in a regime where Tk is large compared to delta. In the other two regimes, there is no Tk. That's the first point. And second, of course, the Tk is not going to be the Tk that we found in the metal case, but rather it will be renormalized by the interaction in the bulk and depend both on J and G. And we need to apply various non-perturbative techniques to study the problem. So I will show, so the model is integrable for any G and J, and what I'm going to show is are the following: that the bulk is gapped, that a delta equals to dE minus pi B, where B is written down here, that's the bulk parameter. It's essentially, for small g, it's 1 over 2g. So that is the conventional gap. And I'm going to have three boundary regimes that depend on the relative values of G and J. I'm going to have a Kondo regime, a YSR regime, and an unscreened regime, moment regime. And these regimes are characterized by a quantity that I'll call A, where A is an RG invariant. Both G and J run with RG, but there is a combination which I call A, and it's written down here. It's a combination of J and G. This combination here is invariant and can characterize the various regimes. So what I have is the regime where sometimes I'll call A, sometimes I'll call it D, because you see the parameter can become imaginary, and if it's imaginary, I'll write D equals to IA. So what I claim is that there is a Kondo regime when this parameter A is less than half or going imaginary. Then I'll have a YSR regime between half and 3/2. And then I'll have the unscreened moment regime here. And this depends on the relative values of J and G, or more precisely, on the values of A. So so in the YSR regime here, I'm going to show that there is an intra-gap bound states, true bound states, and it mediates the first order phase transition. And there is single particle screening. It's not a Kondo effect. It is single particle bound state here, which screens in this regime and does not screen in this regime. And hold on. I'm giving a talk. So this is the YSR regime, and it has a semi-classical description. Then I have a Kondo regime, and that is when the parameter A is less than half. No bound state here. It's a renormalized Kondo. It generates a Kondo scale. It has a singlet bound state. And there will be a very interesting crossover from deep Kondo to single particle Kondo as I'm changing the parameter A from minus infinity, let's say, to half, at which point it smoothly connects to the YSR regime. And then I will show that there is another regime, an unscreened regime, a regime where we have spin half moment, and it will have residual interaction with the gas of electrons, weak interactions.
I have a question, if I may, about
Yes.
YSR phase. I got confused. So why you're saying that there's bound states on one side
Yes.
of the parameter, values of parameter, and there is no on the other, but
And
it looks symmetric for me. So what?
That's right. You will see that the bound state here create a singlet. The impurity is screened, while here the impurity is not going to be screened.
Okay. So it's not obvious from this plot. I thought maybe I should
not from this plot.
Okay.
These are just the energies. Okay, so what I'm going to show is how a quantum fluctuation go from a regime where I start classical impurity and semi-classical bulk, and then, so this is what YSR were doing really, and then I will allow the bulk to become quantum, keep impurity classical, and then I will do the full problem where both the impurity is fully quantum and the bulk is fully quantum. And the message will be that going from here to here, as I allow more and more fluctuation, I'm going to have the full problem, and the YSR regime, which here dominated the full phase space, is going to shrink to a small part of the phase diagram. So let me start with the YSR approach, where the impurity was classical and the bulk was semi-classical. So we take the limit S goes to infinity, holding Js fixed. So this becomes the impurity, the H impurity. And we bosonize the superconductor. When we bosonize it, here are the usual bosonization formulas and the relation between the parameters in the original theory, where G perp goes like the M naught over beta square here. And this is the spin part. And there is a decoupled charge part, which is gapless. And we can do a transformation which removes the impurity and moves it into a boundary condition, so that phi L at phi naught at 0 is 2Js over the beta, while on the left side, where there is no impurity, it's 2 pi over beta over n, which is the usual boundary condition when you have open boundaries. So this is the model now. In the end, we are taking the semi-classical limit, where beta here goes to 0. When beta goes to 0, then we have to look to configuration phi, which minimize the interaction. And these are solitons, subject to this boundary condition. So we have spectrum of kinks and anti-kinks. And we find that the ground state, namely the YSR state, consists of a kink with this energy here and an anti-kink with this energy. And you see that we have, this is all there is. The YSR states, the bound state, psi minus, and the non-bound state, but it is the same behavior, dominate the full phase diagram. And between them, there is a first order quantum critical point. Now I'm going to keep the impurity classical, but allow the quantum, the bulk to become quantum. So now I take the opposite limit. where beta square does not go to 0, but becomes 4 pi. So I restore bulk fluctuation, but I still keep the impurity classical. So at this value, I can refermionize my model, and I get that the bulk is described by a massive Turing model. So it's a Dirac equation this is a famous point first introduced by Luther and Emery in '74. And we get a Dirac equation with twisted boundary conditions. So on the left, we have the usual boundary condition, while on the right, we have a twist due to the impurity. So we have to solve the Dirac equation with twisted boundary condition. And here is a solution. Chi lambda is A lambda. These are the various solutions of the Dirac equation with energy epsilon lambda equals to minus m cos hyperbolic pi lambda. Lambda is a parameter, we call it rapidity parameter. And sort of we have a boundary phase shift at the position of the impurity. So the fermion is reflected at the boundary with this phase transition. And this leads to equation for the lambda, which is written down here. In other words, we impose the boundary condition and we find that EIM sinh hyperbolic pi lambda times L has to be equal to this phase shift. And to find the ground state, then we have to fill all negative energy modes. And then we can study excitations and find that they are gapped. Now, what we discover that the S matrix has 0 poles, namely there are lambda bound states where there are poles, and these poles are the bound state of the YSR theory, but they are only now in part of the phase diagram between half and 3 halves. Then we can have chi bound states of this form with this scale psi a determining the extent of the extent of the state. And it's only renormalized, the bound state is only normalizable if A is between half and 3 halves. So you see that the YSR regime has shrunk now. In the fully classical problem, it was between 0 and 2. Now it's only in this part. Then we now going to go to the next step and do a fully quantum treatment where both the impurity and the bulk are quantum. And we can do that because the model is integrable for any G and J. Again, this is, let remind you, this is the Hamiltonian left-right movers. This opens a gap. And here we can do it only for the model, as far as we understand at this point, is integrable only for the isotropic case. And here is the coupling to the impurity. So here, 2 minutes a summary of the beta ansatz approach. So we are trying to diagonalize this Hamiltonian. We write down an n particle, an electron wave function, so which is obtained by applying n times creation operator to the empty ground state with some wave function f, which depends both on the spin and on the chirality parameter, whether it's right or left mover. And here is this the spin of the impurity. So the way we construct this wave function is we divide configuration space into n factorial regions, within each region, there is no interaction because the particles are not on top of the other. They interact only when they cross. So within these regions, they are free particles, and we can write down plane wave solutions with arbitrary coupling. And what we have to make sure is that when two electrons cross, there will be an S matrix which relates one region to the other region when we determine the S matrix from the Hamiltonian. And what we then can show that this kind of process is consistent if the S matrices that we derive from the Hamiltonian satisfy certain conditions which called the Young-Baxter relations, in which case this procedure is consistent. Then we want to impose boundary conditions, and here we are talking about open boundary conditions, not periodic, because we have at the edge the impurity. So we need to take an electron, bring it to one edge where there is impurity, bring it to the other edge, and come back. So this process is captured by this operator T here, which you see takes us to the one edge and then brings us back to the original position. And then there is beautiful technical part which allows us to diagonalize this this operator here, which translates us, which is the operator which brings us from one edge to the other. And this leads to a set of equations which are called the Bethe-Ansatz equation. And it's given in terms of parameters lambda, which are we call Bethe momentum or momenta, spin momenta, which we solve from this set of equations here. And once we have determined the lambdas, we plug it in here, and then we can determine what is the allowed momenta. Once we have determined this allowed momentum, then we can calculate the energy because it's the sum of this kj, which we determine from this expression. So notice that because we have here open boundary conditions, everything is doubled. You see, we have lambda and we have minus d and plus d, minus b and plus b. That is because at the edge, when we have a k, it is reflected and there is a minus k. So things come in pairs, and that is the Sklianin approach, who set up very nicely this formalism that allows us, instead of doing periodic boundary condition, to solve the systems with open boundary conditions so that we can study the edges or attach various impurities at the edges or magnetic fields at the edges, which gives us a much deeper understanding of this system. And again, the parameters that appear here are B, the bulk parameter, which is essentially 1/2J, and the RD, the RG parameter, which is this combination, which we are going to see is unchanged under the renormalization procedure as we are taking cutoff to infinity.
May I ask you, Natan, for what? This n on the second equation is a power or is an index? I'm confused with n here.
This
you have n times the same scattering?
Where? Here?
On the second line.
Yes.
You have n in a power.
Yes, exactly. So this n is the number of the electrons. Yes.
So it's a number of electrons. The second one is a one single impurity.
This is the single impurity. I'm coming to
And this is a scattering between impurities. Okay. Yeah. So all they have a B. All they have a B, but they
exactly.
Yeah.
So you see ahead what I want to say. So again, these are the equation. If I remove these terms, this is just the bulk terms with the parameter B, which describe the superconductor. And this opens a gap, D to the E minus pi B, that is the bulk scale, the superconducting gap. And that is all in blue. And if I add here these terms, this is the impurity terms coupled now to the bulk. And it's characterized by D, which is the RG invariant. So these are the Bethe-Ansatz equations. And we are going now to discuss the solution for various regimes in D. So D does not get renormalized. B is driven to B is running because this is part of the bulk here. You see, I'm going to hold delta fixed, that is the bulk gap. As I send D to infinity, and B will be going to 0 so that the bulk is invariant under renormalization. And what we are going to discover that the solutions here, there are 3 regimes which depend on the values of the parameter D or A. It's the same thing. So for A, in here we'll have YSR regime, here we'll have the moment regime, and here we'll have the Kondo regime. And each regime generates its own scale. We have the scale, which is an invariant scale, delta times a function of D, and D will take different behaviors in different regime. Here I will show that it generates a Kondo scale. Here there will be a bound state scale, and here there will be, again, a moment scale. So the way one now solves it, one takes this, there is a well-developed technological way. One takes these equations and turns them. One cannot, of course, solve this algebraically, but in the limit of very large n, one can translate this equation into an integral equation for some parameter phi1, which is given here, and rho is the density of solution, which is must satisfy this integral equation. And now I'm going to explain the results of this solution. So here we have, first I'll talk about the Kondo regime, where the parameter A is less than half, and after 0 it becomes what I call D. I have to extract an I. So what we find here, that in this regime, we have a many-body singlet. We can calculate the density of states. There is rho bulk. This is the typical density of states of a superconductor. And here is the density of state of the impurity divided by the superconductor. And we are going to use this scale to define our Kondo temperature as the scale E, where the density of states goes to half its values. So Tk is of the form delta square root 1 over cosh hyperbolic square pi d. And this is valid over the full regime here in the deep Kondo or in any regime. But in the deep Kondo, this becomes very much simplified, because in the deep Kondo, J becomes very large compared to G, and you get the typical Kondo scale here deep in the Kondo regime. While if we are changing D to the value 0, and then to the value half, tk shrinks and becomes of the same order as delta. And then we have the screening of the impurity by bound states, by just very few bound states of order delta. And it's kind of single particle screening, not anymore a cloud. And then it crosses over to a local bound state which screens it. So here there is a smooth crossover from multi-particle screening to Kondo scale that shrinks to a delta, that is the single particle screening, and here it crosses over to screening by local bound states. So in the YSR regime, how am I doing on time? Okay, I'm good. Here I am crossing over to the YSR regime between when A is between half and minus half. So no longer Kondo cloud. Here we have single particle a bound state which screens the impurity. In the language of beta ansatz, what I have is a closed strings, namely lambda bound state, which is purely imaginary, and it screens the impurity here. And when A is less than half, namely here, the ground state has a bound state and the impurity is screened as Z is equal to 0, while here, in this regime, there is no local bound state, and as Z is plus minus half, the lambda bound state is does not exist, and therefore the impurity is changed. And now we are going to the wide, again, that's a technical statement. When A is larger than 3/2, the lambda bound state is of this form. It is not does not screen anymore, and it's a solution. So now I have local excitations coupled as plus minus half to the screens, and we have a doublet ground state plus half and minus half. We have no YSR, but still we have residual scales, and as Z, if I apply a local magnetic field, will have a magnetization if the local magnetic field is larger than twice the gap, and then I have a typical square root singularity, and we have a new scale generated, f of A, which is given by this expression of dilogarithms. So let me summarize then that the Kondo effect in 1D superconductor, and as I did, I increased the fluctuation from semi-classical to fully quantum. And when I have purely semi-classical, then the whole phase diagram is exhausted by the YSR bound states, and actually not bound state, YSR state, they are bound state only here. And I have a semi-classical description valid, and I have two phases, screened and unscreened. While here I have, in the full quantum regime, I have three regimes, Kondo, YSR, and unscreened. And the main feature, the main message is that the quantum fluctuations destroy the YSR. Here it was over the full phase diagram. Here it remains only on small part of it. Okay, we can now generalize the model and have two impurities, one on the left, one on the right, with each of them having its own coupling constant. So I have J left and J right. So now I have three parameters, the coupling constant in the bulk and two independent coupling constant. And as a result, I'll have two RG invariants, A left and A right, and the model is integrable for any value of JR, JL, and G. So I'm getting a very rich phase diagram. So this is the AL on the left, this is AR on the right. I have here various YSR regime. I have Kondo, unscreened. I could give a full talk only how one moves along in this phase diagram. I will not do that. I just point out that we have all kinds of very interesting physics. For example, at the point around here, we have a supersymmetric algebra, SPL21 cross SPL21 algebra relating left and right states. And we don't understand how SUSY appears there. So I don't want to discuss that. So, but I want to discuss another aspect that I mentioned already in the beginning. What happens when we put magnetic field on the two edges? So I apply magnetic field to the left and to the right. And what I claim is that something very interesting will happen, will push the system into a topological phase, which supports fractionalization at the edges. So here is again, here it's the superconductor in the spin singlet phase, spin singlet superconductor, we are here. And when I apply a magnetic field at the edges, I will drive it into behaving as though it was on this line. And the argument is very pretty. When I apply a magnetic field, it's like twisting the model and applying a twisted boundary condition rather than open boundary condition. So this is the magnetic field at the right edge, where I did not put yet any magnetic field on the left edge. And for very large magnetic field, this twisting boundary condition is like the operator sigma z. Now, if I have a large field, then it is like applying a duality transformation on the model. So psi L goes to psi L hat, while psi R goes to psi R times I sigma. And that maps the SSA, the spin singlet Hamiltonian on this line, to a spin triplet Hamiltonian on this line, because it's equivalent to mapping G perp to minus G perp, going from here to here. And as a result, what we claim is that at the edge of the superconductor, we'll have fractionalization and spin quarters would appear. So let me explain this appearance of spin quarters. First, I'll do it semi-classically, and then I'll do it fully quantum. So semi-classically, I do the usual semi-classical, I bosonize, and I take the semi-classical limit. And now notice, if I have open boundary condition, then the phi charge on the left and is going to be 0, but on the right, it will be square root of pi over 2, while the spin on the left, a spin field on the left is locked to 0, while on the right, it will be determined by the total spin of the system. This is not Dirichlet. And here, when I take now the semi-classical limit, beta goes to 0, I have to be, the ground state has to be at a value to minimize the cosine at pi over 2. But the boundary condition forced the field to twist either to 2 pi beta or to 0. So you see, here I have a ground state, and the field configuration, in order to satisfy the boundary condition, has to twist either up or down. So I have 4 states. From this ground state, I can have on the left going down or going up, or on the right going down or going up. Now, so you see, I have the field configuration here. And remember, the field configuration is related to the total spin by this integral here. So I carry out the integral, and I discover that this carries spin quarter and spin quarter. So at the edges of the superconductor, we find fractionalized spin of quarter, value quarter, plus minus quarter, and plus minus quarter. Now I can, so this is a semi-classical. Now semi-classical, you can worry that you were studying the limit beta goes to 0, so you are in this regime here, while we want to calculate the model when we start not at the large value of G parallel, but small value, namely in the fully quantum strong fluctuation regimes. And then we can, again, solve this model exactly. And what we find is, from doing the beta ansatz, that in the ground state, I have plus minus half excitations. That is just when all lambdas are real. And we have 2 more solutions when lambda is plus minus half. Remember, plus minus half is just, I have to count it as 1 excitation because I'm doing it with open boundary condition. So k and minus k is the same. I count it the same. So lambda plus minus half gives me a singlet. And there is another singlet, again, close to it, which I can identify by a little bit twisting the boundary conditions. So we find then that when we do this calculation, in the spin singlet superconductor, we have no string solution, and there is a unique ground state equals to 0, while in the spin triplet superconductors, I have 2 degenerate ground state plus minus half and 2 singlets, which correspond to these string solutions. So we interpret this as quantum edge kinks with fractional spin as z equals to quarter. So we have plus quarter at the right-hand side, plus minus quarter on the left-hand side. So what we find is the Hilbert space of edge kinks classified by the total spin as z plus minus half and 0, which is the sum of the excitations on the left and on the right. So the 2 states that we found with SZ equals to 0 are given by plus quarter on the left, minus quarter on the right, and the other one is minus quarter on the left, plus quarter on the right. And the 2 states, I'm sorry, the other way around. These are the 2 states, the 2 singlet states, while the 2 spin half states are half here, a quarter here and quarter here, and minus quarter here and minus quarter here. Altogether 4 states, fractionalizing the spin at the edges, and that is one of the hallmarks of the topological, being in a topological non-trivial phase. And this can be verified by the MRG calculation. You see that you get here, for example, a quarter up, quarter down, or that is the yellow, or quarter down in blue, and at the edges. And what we did is also study those the variance and show that the variance vanishes. So these are genuine quantum objects at the two edges. So applying a magnetic field at the two edges of the superconductor forces the Kondo spin to act as dual transformation, which maps the model from being in the A phase to an A dagger, A hat phase, where it becomes a topological model, topological state. So the two impurity model, let me summarize, has quantum fluctuation at the edges, and that leads to what is called a spin-protected topological phase with entangles the two edges, and it leads to a appearance of fractionalized charge. If we, on the other hand, do not apply a field and we maintain the SU2 symmetry, then we have enhancement of symmetry at the edge and at the boundaries, and we get supersymmetric algebra, which when we break, again, we reduce the supersymmetry into a Clifford algebra, which supports a spin accumulation at the edges of SZ plus minus quarter. And we can construct Majorana modes, and that's what makes this model very attractive to storing quantum information, Majorana modes that map excitations on the left to excitations of the right. So let me summarize. I showed that YSR states are mostly destroyed by quantum fluctuation. They facilitate, however, a quantum phase transition at the center of the phase diagram. We obtain a renormalized Kondo regime and a renormalized moment regime in different parts of the phase diagram. And the quantum fluctuations at the edges lead to an SPT phase, to a topological phase entangling the two sides, and existence of Majorana modes. So that's it. Thank you very much.
Thank you very much, Natan, for this nice primer of integrability in Kondo model. And we can pass now to questions. So please raise your hand and ask your question. Hi, Angela.
Hi. Hi,
Oh, hi, Angela.
Hi, how are you? So nice to see you. So very nice talk.
Unfortunately, I don't see you. Hold on, let me stop sharing.
Good.
Oh, now I see you.
So how are you? So very nice talk.
Thank you very much.
You can also turn on your camera, Natan. I think we would.
I turn. You don't see me?
Oh, sorry. No, we see you actually. Sorry, you just.
Yeah, I have some questions first. First of all, I'm very happy to see the power of the Bethe ansatz in your solution. So just a more mathematical question. When you solve the Bethe ansatz equations, have you checked or looked about the completeness in the examples?
I don't know how to show complete. Well, I'm sure it's complete. And my argument is that when you calculate the S matrices, they are unitary and they behave properly. But if you ask whether I counted them, I did not.
And now going a bit more to physics, for example, you have shown your results highlight the role played the quantum fluctuations in the physics of YSR states in this specific example, one-dimensional charge-conserving superconductor. Can you extend your derivation to systems with multiple impurities? You mentioned 2 impurities, also to higher dimensions or to non-conventional other superconductors? So 3 questions.
Well, yeah. So as you know well, we don't know how to go to higher dimension. And then you need other approaches, and typically perturbative or numerical.
Yes.
And people did NRG calculation and so on and so forth. So there are them. Now, multiple impurities. So now that is a problem that we are actually working on, how to put impurity not at the edges, but in the bulk.
Yeah, exactly.
And that is, we already have some results, but not yet. Even one impurity in the bulk, now you need to take into account a scattering of the, not only right to right and left to left, but right to left and left to right.
Yes.
When we are at the edges, it comes in naturally because the boundary condition. But now when you have it in the bulk itself, then it's a new.
Yes.
But we are working on that. Of course, this is a very interesting question.
Yes, this would be very interesting to have.
Of course, it would be even more interesting if you put 2 impurities, 2 Kondo impurities, and then you can have RKKY interaction, and you have a lot of fun. Yes. But this is still open.
Very rich phase diagram, probably. Right?
Yeah, exactly.
And can you extend to other non-conventional superconductors?
Yes, P waves we can. I don't know yet about D waves or other. We can extend it to higher spin Kondo, and we are trying also to understand. So one way of thinking about the impurity in the bulk is to have it coupled, let's say, to 2 wires. And sort of in the middle and coupled to 2 wires, and it would be like a 2-channel superconducting model. So the physics of a multi-channel or 2-channel Kondo combined with superconductivity would be very interesting.
So you are working the simpler model, and then you can extend it on. First, you have to fully understand this case.
Yeah.
So very nice. So nice to see you.
Nice to see you. You are at your home institution.
Yeah, I am in Brazil, in Porto Alegre. Rio Grande do Sul, the top is in Rio Grande do Norte. We are in Rio Grande do Sul.
It's amazing. You don't know where people are.
Yeah. Yeah, we have to make a big conference in Natal again.
Yeah, it would be great. We had a very nice time in the last meeting.
Yeah.
It was great. It was great. Yeah.
Yeah, right.
All right. Thank you, Angela, for your questions. There is one raised hand by Tiago. Tiago, please ask your question.
Hi.
Hi.
Thanks, Nathan, for the great talk. I have just a clarification. You had some, in one of your results, you have some square root singularity. What is the meaning and the formation of the singularity?
Where exactly?
You had some spins, and you mentioned that there is some square root singularity. And
that is, yes. You mean here?
Yeah, I missed it. What's the meaning?
Yes. That is actually straightforward.
So we cannot see your slides now. You need to share the slides again.
Okay.
Let me do that.
Hope now it will work.
Hold on. I have to end show. Okay. And I have to just this square root of singularity is in the presence of the magnetic field.
Okay.
Just a second, let me.
So,
It's a transition, essentially. A square root of transition with magnetic field, essentially.
okay.
Yeah.
It's a standard square root. Square root of
standard
having
square
a
root.
massive. When you have a massive particles, it's a
okay,
general.
okay.
Exactly.
So, it is
Because
something that I missed.
because you have to have enough energy to put in the magnetic field to overcome the gap.
Okay.
Right? And you have to break a pair, and then it's a pretty standard square root singularity in a superconductor.
Okay.
Square root. I have one question. Sorry. First, maybe I missed Natan, but I missed a moment. Is it this decoupling in the quarter spins happens for arbitrary magnetic fields, or the magnetic field should be more?
It is strong magnetic field.
Strong magnet, but you don't have critical some parameter to when does it disappear essentially, or have you transition or not?
That's a good question. Well, now, if I talk about the pure superconductor, then I have it for any magnetic field in the pure superconductor. I'm sorry. So I'm not saying it precisely. In the pure magnetic field, in the pure superconductor without Kondo, when I put magnetic field at the edges, then
arbitrary field you have effect.
Yeah. So only superconductor without Kondo. Then, and I put magnetic field at the edges, and then it's only for, it behaves like a twist operator, twisted boundary conditions. So this twisted boundary condition, now I know how to study them at two universal values with zero magnetic field, when the parameter there is in some units either 0 or pi over 2. Then these are two boundary conditions. Now you are asking how to do it in the intermediate way. Then it's kind of a mixture between the two regimes. I can solve it for any value, but it's not a clear behavior.
Okay.
Because you can solve the beta ansatz for any twisted boundary condition, but the interpretation is the simplest in the two values that I mentioned.
And one more question, very short. Do you try to entangle Kondo spins? So essentially, you connect ends of the system and take the spins close to each other.
So, no. That's totally different physics. Here, the physics is that they are actually very large compared to each other. So, for example, I said that the quarter spin, the four states are degenerate, namely quarter up, quarter down. But this is true only when when the size of the system is very large. The reason is that to go from a quarter minus quarter to plus quarter, I have to change the parity of the system, add an electron, and that means that in the sector of the charge, I have charging energy, one over L. Yeah. So now you are saying, suppose I have maybe the system very large, but I twist it together and couple the two spins with each other. That's a very interesting system, but actually we are studying a related system where we have two Kondo systems which are coupled together. but
Yeah, it's almost the same.
but not we are not doing it in the superconducting regime. We are doing it in the regular regime,
Okay.
the regular Kondo.
Thank you. Thank you. Thank you for very good talk. Very interesting. Thanks a lot.
Thank you.
Okay. Are there other questions? Fabio, please, you can ask your question.
Thank you, Dimitri, for the word. Natan, great talk. Since I met you here in Brazil in 2009, nice to see you again.
Nice. I don't see you.
I am in the other. It's just because of my video. In my notebook, there is not.
Now I see you.
Right, yeah. You can see me. Okay.
Yes.
Look, great talk, very clear physics. At the end, you mentioned about the preserving of the SU2 symmetry and the enhancement of the symmetry when you consider two quantum impurities at the edges, at both edges. Yes. I was wondering what you can infer about the charge sector in the enhancement of the symmetry, because when you say about the SU2 symmetry, I figure out the spin sector, right?
This is the spin sector. The charge sector is decoupled, and it's not affected by this.
Oh, okay.
This is a model which charge and spin are decoupled. This is how the system is able to generate a gap without breaking a symmetry. It's by the decoupling of the charge and spin. So in the charge sector, I don't have anything except charging energy.
Right. So this this enhancement in the symmetry, has you figured out this enhancement?
That's a very good question. I don't know. I don't understand that. The symmetry suddenly is very large, and why it is, we are still trying to understand. We don't understand that yet.
Right. Thank you for your consideration.
Supersymmetry appears out of nowhere. I don't know what it means. Accident or I don't know. I shouldn't say what.
Right. Thank you for your gentle attention, as always.
Thank you very much.
Thank you very much, Fabio. Well, I don't see other questions, so let me just ask. You mentioned experiment in the beginning, so do you have expectations about seeing this kind of Majorana modes in experiment?
I hope so. You know, people are chasing Majoranas.
but the fact that this is a one-dimensional system, is it a problem, or is there like any proposal for experiment in this case?
Yes, there are proposals. There are proposals. For the Majorana, now if we forget Kondo for a minute, so Majorana at the edges of a superconductor, so that was proposed originally by Kitaev in non-interacting model, and there are proposals to see that, proposals where you take a wire on top and induce superconductivity through induced superconductivity in the wire by putting it on top of a bulk superconductor. And you can show that you will induce a P-wave superconductor this way with theoretically with boundary Majorana at the edges. Now, several people have announced that they have seen it experimentally, and several people have been very embarrassed when it turned out that the data was manipulated. And so the answer is, a lot of people are trying to see that, but it has not been seen. but everybody believes that it will be seen. There are experimental difficulties. So, but there is no doubt, nobody said that they are not there. It's just hard to observe.
Well, so in your model, they're quite robust because they're predicted by integrability.
Exactly. Exactly. So they should be there, and but you know, you need a wire which is precisely described by this. So theoretically, it's easy to see, but experimentally, not so easy to realize. But in principle, everything that I discussed should be realizable in nature. And in a sense, the fact that you have a superconductor makes it even more robust, because dirt or impure or non-spin-like impurities don't interfere with the process. There are some theorems by Anderson that argue that as long as you don't have magnetic